Hi, I'm Trapit, and I'll talk about how we can make fine-tuning of natural language models on few-shot data both parameter efficient and accurate. So we're interested in few-shot learning, which is this remarkable ability shown by humans where they can generalize from just a few examples of a never-before-seen concept. For example, given this one instance of an object category, one can easily identify which of these other objects are likely to be from the same category. Similarly, given this one instance of a relationship between two entities, you can easily identify which of these other entities have the same relation. Now, as machine learning models have become more capable, few-shot learning is starting to transition from being just a desirable hypothetical concept to something that has wide applicability. For instance, one area where few-shot learning is very useful is for end users of a cloud-based machine learning service, where we want to provide general-purpose models that many customers can potentially use for their own tasks. Such users will often have limited label data for their task and will also have limited resources to collect more data or invest in training their own machine learning models. So existence of a cloud-based machine learning service that can serve highly accurate models that can perform few-shot learning is very desirable. So then the natural question is, how do we get models that are good at few-shot learning? One approach that has been very successful in NLP is pre-training. The idea behind pre-training is to train models on massive amounts of text data that is naturally available from the internet. The pre-training process enables generic language learning that is useful when solving new tasks that have limited data. And once the model is pre-trained, it can be further fine-tuned on the task of interest using the data available for the task. As it turns out, this pre-training followed by fine-tuning approach can be very effective at solving new tasks. Now, such pre-trained models can be served in a cloud-based service to end users who can perform the tasks that they're interested in by fine-tuning this pre-trained model on their tasks. However, this scenario is completely impractical, as this makes a copy of the parameters for every task for which the model is fine-tuned. And since the pre-trained models are typically large, this leads to prohibitive storage costs for serving such models. So we are interested in how we can make this fine-tuning process more efficient such that it doesn't make a complete copy of parameters for every task. One recently proposed idea to enable this is adapters. And the idea here is to introduce a small number of randomly initialized parameters between each layer called adapters. Then for each task, only fine-tune the green adapter parameters and keep the pre-trained model frozen. Since the number of adapter parameters is a small fraction of the total pre-trained model, it doesn't have as prohibitive a cost as fine-tuning the entire model. However, one problem with adapters is that they're randomly initialized, so they need sufficient training data to work well. And as we'll see in evaluation, adapters don't perform well on few-shot fine-tuning. Thus, in this work, we ask the question of how we can make adapter fine-tuning work well on few-shot data. For this, we cast this problem as a meta-learning problem. The underlying idea in meta-learning is to train models in the same way that they're supposed to be used later. So since we want the models to be good at few-shot fine-tuning, we're going to use meta-learning and train the models in a way that they're good at few-shot fine-tuning on unseen tasks and also parameter efficient. To do this, we introduce meta-adapters. So consider a pre-trained transformer model. And here we can see one layer of the transformer model visualized. This is now the transformer layer with adapter modules added to it. So on any new task, the way adapters work is that you will keep the pre-trained transformer layers frozen and only fine-tune these green adapter modules on the task. This now shows the meta-adapter architecture. So meta-adapters are these feed-forward modules that sandwich every adapter in the layer. Meta-adapters are frozen parameters. That is, they're not fine-tuned on any new task. And these meta-adapters condition the activations of the model in the forward pass and the gradients on the adapters in the backward pass. We'll use meta-learning to train these meta-adapter modules, keeping the base model frozen in such a way that fine-tuning the adapters improves few-shot performance. Note that since we only fine-tune adapter modules, this approach has the same parameter efficiency as that of vanilla adapters. Now, the main benefit of meta-adapters emerges from their meta-training. These modules are trained using an approach similar to model-agnostic meta-learning or MAML. So given a few-shot task, we fine-tune the adapters on the training data for the task. Then we use the performance of the fine-tuned model on the task validation set as the signal to train only the meta-adapter modules. Thus, the meta adapters are trained explicitly to improve the few-shot fine-tuning performance. There are a couple of additional advantages of this approach. So in addition to learning the meta adapter modules, it also allows us to learn initializations of the adapters and the learning rates for fine-tuning the adapters in each layer. This removes the need to set these important hyperparameters at test time, which is a big benefit as we do not have enough data to do a hyperparameter sweep for each few-shot task. Now, an important requirement for meta learning is the distribution over few-shot tasks for meta learning. So where do tasks come from? We use this prior approach to create few-shot tasks from unlabeled data. This approach creates a very large distribution of bank-filling few-shot tasks from completely unlabeled data to allow large-scale meta learning. And in addition to millions of such self-supervised tasks, we use a small number of real NLP tasks from the GLUE dataset. A combination of these tasks then serves as the task distribution to enable meta learning of the meta adapters. So let's look at some evaluations to see how well meta adapters perform. We used a benchmark of 17 classification tasks for evaluation, which come from these prior work. None of these tasks were used for any of the models during pre-training or meta training, and they often differ from the training tasks, both in the input domain as well as the target classification labels. Each task only has K examples per label for training. So we fine-tune models on the K examples and then evaluate them on the full test set for these tasks. Now we consider many strong baselines, and all baselines use the same underlying pre-trained model, so results are comparable. The first baseline is fine-tuning vanilla adapters. The second is adapter fusion. This is a state-of-the-art adapter method that fuses multiple different adapters for better transfer learning. The fusion adapters used in this method were also trained on the GLUE tasks. The last baseline is a full meta learning approach from prior work that uses meta learning to retrain the entire pre-trained model to be better at few-shot fine-tuning. This approach fine-tunes all parameters for every task and is not a parameter-efficient approach. Thus, the goal will be to get performance comparable to this model while only fine-tuning a fraction of the parameters. So let's look at the results. We'll look at the average accuracy across all few-shot tasks in the evaluation on the y-axis. And on the x-axis, we have the number of parameters that are fine-tuned for every task on a log scale. We'll see results for 4-shot, 8-shot, and 16-shot. So in general, we want to be as much towards the left as possible for parameter efficiency and as much to the top as possible for accuracy. Here are the results for hybrid SMLMP, a meta learning model which fine-tunes all parameters for every task. It is quite accurate, but as expected, it is not parameter efficient. Now we can see the performance of adapter fine-tuning. It is parameter efficient, however, it is quite a bit worse in few-shot accuracy. Now we can see the adapter fusion baseline. It is much better than vanilla adapters in few-shot accuracy, but it is also not very parameter efficient, primarily because the fusion modules have many parameters that are fine-tuned for every new task. Now we can see the proposed meta adapters. It is much more accurate than the baselines for few-shot learning. And compared to the meta learning approach that requires full fine-tuning, meta adapters only fine-tune a very small fraction of parameters and achieve comparable accuracy. Thus, meta adapters lead to both parameter efficient and accurate few-shot learning. Now, an alternative to fine-tuning for few-shot learning is prompting, which has gained a lot of popularity. This involves providing the few-shot task in natural language to a large language model, and then generating a natural language prediction for a test instance. However, such methods typically only work with very, very large models, and fine-tuning such giant models can be impractical and unstable. Thus, they are typically only used with prompting. We compare few-shot prompting for a large language model, GPT-3, against few-shot fine-tuning with meta adapters on the BERT model, which is many, many orders of magnitude smaller in size. You can see the performance here across a set of evaluation tasks. Even when using much smaller base models, meta adapter fine-tuning is better on average than all the first 3 GPT models, all of which utilize much larger transformers. Interestingly, we find that on average, meta adapters are also competitive with the largest GPT-3 model. So to summarize, meta adapters are frozen networks added to a pre-trained transformer that condition it to be better at few-shot fine-tuning. Meta adapters enable parameter efficient few-shot fine-tuning by only fine-tuning a very small fraction of the pre-trained model parameters. They are also competitive with few-shot prompting of much larger GPT-3 models while only utilizing smaller pre-trained models. Please check out the paper for more details and results. Thank you for your attention.